So, welcome to this class on monosynaptic and other reflexes. So, most of this is going to be monosynaptic reflexes. So, we have been discussing in the last two classes the case of monosynaptic reflexes. In today's class, we will discuss two other things. We have introduced these notions earlier, the concept of 1A interneuron and the special inhibitory interneuron in the motor circuit, it is the Renshaw cell, and in today's class we will talk about 1B interneuron. We will talk about stretch reflex, alpha gamma coactivation, how these reflexes can also be modulated by descending influence or those that involve brain circuits or what are also called as long loop reflexes. Let us remind ourselves of this case of the monosynaptic reflex. What does this do? This resists the lengthening of a given muscle. So, if a muscle is stretched or lengthened, the muscle spindles 1A afferents fire and cause contraction or they excite the alpha motor neurons of the same muscle and cause contraction or prevent stretching in some sense. For a long time, for centuries, it was thought that this is actually a property of the muscle. This is like a passive property, this is not related to control. For a long time this was believed. Only just about 100 years ago, it was found that if you transect the dorsal roots, right, if you transect the dorsal roots, this response disappears. So, if you cut the dorsal root, what happens is there is a big difference between the dorsal root intact. When the dorsal root is intact, this is what is found, right, and when the dorsal root is cut, this is what is found, big difference. So, this means that the dorsal root is absolutely necessary for this function. This was first, and as the muscle length is changing, so the muscle length is increasing. So, the muscle length is or the muscle is stretched. As the muscle is stretched, in the presence of an intact dorsal root, you are going to have a relatively strong response such as that. If the dorsal root is cut, even though there is a stretching, the response is going to be relatively weak. This means that dorsal root is essential, at least forms an essential part of this. From Liddell and Sherrington, you have to see the year just to give you a context, 1924. Okay. So, this is data from 1924 from Liddell and Sherrington, for the first time showing that the information coming from the dorsal root plays an important crucial role in modulating the reflex responses. So, this means that that is how we realize the importance of 1A. So, there was even a question as to how do you know that this is how it works. Many of these things are not seen, the neurons are not seen, these are just pictorial representations. So, this picture for example is a pictorial representation of our impression of what is going on. What is actually going on is not exactly seen, but understood through latencies. This is classic neurophysiology, understood through latencies. If you excite 1A afferent at the dorsal root, the response at the ventral root of corresponding alpha motor neurons is found at approximately slightly less than 1 millisecond. And since we know that the synaptic transmission is about 0.5 milliseconds to 0.8 or 0.9 milliseconds, we know this must essentially involve a monosynaptic pathway. So, many of these things are found through accurate measurements of latencies. By computing these latencies, we are able to come up with how many synapses are involved in this process. So, this is how it is done. Okay. So, what is the use of all these reflexes? A slight deviation from the topic. What is the use of all these reflexes? You see, reflexes provide in some sense a crude response, a response to a stimulus, right. It need not be, you know, perfectly acceptable to the context, but it provides a response. In many cases it is performing some protective function. In other words, it is, for example, if there is a painful stimulus, let us assume that this is a, you know, a nail and I am placing my finger on it, or this is a hard object and I am placing my finger on it, right. If it is only slightly hard, I am going to place and, you know, withdraw. Note the point at which the sensory information is collected is at this point, which is the finger. It is not the finger alone that is withdrawing. You see, the response is found here, is it not? The response is found at proximal, more proximal sites, leading to a relatively quick withdrawal from the painful stimulus. If it was very hot, let us assume that it was very hot, actually many more muscles are activated, leading to a complete withdrawal. Like for example, the response could be like that. Of course, this particular example that I am giving obviously involves polysynaptic pathways, it is not monosynaptic. In other words, this response is activating circuitry that activates multiple muscles, is it not? Because the activation involves, you know, withdrawal at the elbow, at the shoulder, at the wrist, etc. multiple joints, that means multiple muscles must be activated. Obviously it involves polysynaptic pathways, not monosynaptic, that is okay, but still we should remember that this is also considered a reflex, or this is also called as the flexion withdrawal response, right. So that means it also involves coordination of multiple muscles. It does two things. First is it activates the flexors, or and inhibits the extensors. So there is simultaneous activation of one group of muscles and inhibition of the other group of muscles. Not just that, there is more. Suppose this painful stimulus is on my leg, on my right leg. Say I am walking and there is a nail, and I am, let us say that I am not wearing a footwear, I am at my home or whatever, I am not wearing a footwear, I am walking, there is a painful stimulus, right. What happens is that, you know, immediately I withdraw the leg by flexing the knee, flexing at the knee, but that means the extensors are inhibited, flexors are activated. What happens, that is at the right leg, is it not? Because the painful stimulus is felt at the right leg. What happens at the left leg is the opposite. At the left leg, what happens is the extensors are activated and the flexors are inhibited. Why? Because I have only two legs. If I remove the right leg, the entire load of my body, the entire weight of my body is going to be rested with just one leg. So I should ensure that that is going to get the maximum support. That is possible by ensuring that the extensors are activated. So let us remember what is going on. It is a bit more complicated than what is shown here. So what is happening is simultaneous activation of flexors and inhibition of extensors of the limb that is experiencing the painful stimulus, and this is called as flexor withdrawal response, okay, a polysynaptic response. The other case is the crossed extension reflex, in which case you know, the other limb, the limb on the other side of the body experiences you know, extension, okay. More details on this, just wanted to give why these things are even being studied, just wanted to talk about that a little bit, okay. And let us remind ourselves of what the 1A inhibitory interneuron does. So the 1A inhibitory interneuron is activated, is excited by the 1A afferent and is inhibited by the Renshaw cell, okay. What it does is it regulates contraction in the antagonist muscle. So if the muscle of interest is biceps, 1A inhibitory interneuron that receives inputs from the biceps regulates contraction of the triceps, okay, of the antagonist muscle. So, let us also remember there are so it receives multiple inputs, not just from I have only mentioned two sources, right, not just from the Renshaw cell and not just from 1A afferent, it also receives inputs from the descending system, and that can both be excitatory and inhibitory from corticospinal and other descending pathways. So, there are multiple inputs. So, but there is only a single 1A interneuron, right, or there are groups of these 1A interneurons. So, these 1A interneurons, there must be a balance of excitation and inhibition depending on in which direction this balance is tipped. It could be tipped in favor of excitation or it could be tipped in favor of inhibition. Depending on that, excitation or inhibition of of the muscles innervated by this, of the neurons that are affected by this will happen, okay. So, this balance must change. So, a change in the balance allows the interneuron to coordinate muscle contraction. So, this is like coordination happens through multiple balance of multiple pathways. So, from 1A afferent, from Renshaw cells, from corticospinal pathways, and let us also remember we discussed some time ago monominergic inputs from the brainstem, etc., etc. All these things are received. By the way, monominergic inputs go to the motor neuronal pool, but the motor neuronal pool itself is inhibited by 1A inhibitory interneurons. So, lots of things, all these things. So, there is just a balance that is reached depending on what the balance is, depending on where the equilibrium is settled at a given point in time, the response will be determined based on that, okay. And we discussed what are these Renshaw cells. Renshaw cells are interneurons that produce inhibition of the neuron that excites it, and also the motor neuronal pool of the synergists, right. So, if biceps is contracting, its Renshaw cell will inhibit biceps brachialis and brachioradialis, all its synergists and their gamma motor neurons, okay. These interneurons are excited. So, that means they are excited by collaterals from several motor neurons, right. So, by the way, let us also remember when brachialis and brachioradialis are contracting, it will inhibit everybody, it will inhibit brachialis, brachioradialis and biceps. So, it will inhibit all the synergistic muscles, okay. They also, so they send collaterals of synergist motor neurons, and they also inhibit 1A inhibitory interneurons of the antagonists. So, let us remember 1A inhibitory interneurons inhibit the function. So, causing what we discussed this earlier, we call this as disinhibition, or in a way they excite or they increase the probability that the antagonist muscle is going to get excited. Another form of negative feedback, we saw this earlier. They also receive the inputs from the descending systems. They also, Renshaw cells also receive inputs from the descending system. So, their excitability are modulated. So, it is possible to adjust the excitability, the probability that the Renshaw cell will be excited, okay. And what is not discussed is the case of 1B interneuron. 1B interneuron, let us remind ourselves what are these cases. 1A and 2 are muscle spindles, and 1B is coming from Golgi tendon organs. When will this be activated? Whenever a muscle is contracting. If a muscle is contracting, the tension in the tendon is going to increase. When the tension in the tendon is going to increase, the Golgi tendon organ is going to get activated and send proportional inputs through its afferent, and its afferent is called as 1B neuron, is it not, or called as 1B afferent. This 1B afferent, so that means what, that muscle is contracting, then its negative feedback must be to relax that muscle, is it not. That means I should inhibit the alpha motor neuron that excites that muscle. Let us consider a single muscle, let us consider say the biceps, right. if biceps is contracting, its 1B afferent will find a way to inhibit the alpha motor neurons that contract the biceps, but let us remember that all proprioceptors by definition are excitatory, they always excite. So that means I cannot directly inhibit the alpha motor neuron. So what this does is that there is an interneuron which is called as the 1B interneuron. So the 1B afferent excites a 1B interneuron which inhibits the alpha motor neuron of the same muscle. So unlike the 1A case, in the 1A case stretching activates the 1A afferent and it excites the alpha motor neuron of the same muscle, causing it to contract, okay. That is a monosynaptic response. In this case contraction activates 1B afferent and we have to inhibit the alpha motor neuron. For that to happen, it cannot do it directly, it activates a 1B interneuron which inhibits an alpha motor neuron, okay. So this is a disynaptic pathway. Okay. And so that means this disynaptic pathway is inhibiting disynaptic inhibition of which muscle, not the opposite muscle. Inhibition of the opposite muscle is performed by the 1A system. Inhibition of the same muscle are homonymous. Same muscle is happening. Same muscle is inhibited. Okay. And but the 1B interneuron is receiving inputs not just from 1B afferent but also from other sources. There is a great amount of convergence of information that comes from various other sources leading to flexibility of responses. Please do read about this, okay. So here is the example. So there is a the Golgi tendon organ here that is detecting the contraction of this muscle. So you want to relax this muscle. So that is achieved through, so that is the, so through an interneuron that is inhibiting this, and the alpha motor neuron is inhibited, okay. Now what also happens is the special case of locomotion versus resting. I said that this system 1B system receives inputs not just from the 1B afferent but also from multiple sources. It turns out that depending on the state the response can vary. What actually happens during rest, between rest and locomotion of a healthy animal, healthy mammal, say a cat is walking, so for example, at rest the 1B afferent causes inhibition of the homonymous muscle as one would expect, right. But during locomotion what happens is that there are others who come into the picture, there are other excitatory interneurons that come into the picture that cause the same 1B system to, or the 1B afferent to cause an excitation in the extensor. So this is called as, this phenomenon has been widely studied and lots of data available on that. This is called as the state dependent reflex reversal. So the sign of the reflex can be changed depending on the context. If I am lying down or if I am sitting in a chair, right, the reflex response is going to be something, whereas if I am walking, for the same stimulus the response is going to be of the opposite sign, sign as in SIGN sign, is going to be in the opposite direction. This is called as the state dependent reflex reversal, especially shown in the 1B system, okay. Please do read about this, discuss how are these things even studied how to study this. Sherrington invented a method to study these things. He called this, we will discuss the various preparations of animals that are studied in a future class, but however I will just mention that Sherrington invented what was at that time a novel method to study the stretch reflexes. It turns out that if you transect the brainstem between the superior colliculus and the inferior colliculus. So, at the level of the midbrain between the superior and the inferior colliculus, if you cut the system, then what happens is the reflex responses or the reflex inputs provided by the brainstem are usually heightened. So, causing great amount of extensor tone or an amount of rigidity called as decerebrate rigidity. Even with the intact animal, you do not have so much extensor muscle tone, but when the cut is made at that particular level between superior colliculus and the inferior colliculus, you will see that there is a great amount of extensor muscle tone that is sufficient for the animal to support its body weight. Remember, this animal has been cut from its brain, from its cortex, from its motor cortex. So, you would expect that it will go limp. That is not what happens. Its body weight can be supported by this muscle tone that is produced from the brainstem. This rigidity Sherrington called greatly as famously as the decerebrate, that is decerebrate rigidity, okay, with the E. Google this, I mean definitely Google this, a nice very beautiful paper in which he discusses. It is also wonderful to read his language of how he describes the situation, okay. So, in that case what happens, the reflex responses are heightened. So, then you can study, you can modulate, you can give specific stimuli and study the responses. The responses are going to be of a higher amplitude than what you would find in an intact animal. This was the invention made by Sherrington way back about 100 years ago for this. So, again an experimental approach, more details and other such preparations in future class, in one particular future class, okay. Another thing that is of interest for us is not just this, there is more, it is not only inhibition of the opposite muscle that is always desirable. Let us say that I am making a particular movement, I want to excite the muscle that is responsible and I want to inhibit the muscle that performs the opposite mechanical action. This is what you would usually consider. Yes, that is an efficient approach, yet there are times when you want to increase the stability or stiffness. In such cases what happens is that you are interested in contracting simultaneously both the agonist and the antagonist, thus increasing the apparent stiffness at that particular joint, right. If I do that, then what happens, well, this is something that you could experience. So, I want to ensure that, suppose I am keeping my arm like that and I want to ensure that nobody can push me away, then what do? I activate a whole number of muscles, both the agonist and the antagonist on both sides. When I do that, if there is a disturbance, I am going to come back to that the original state. So, or we want to reduce the probability that we are going to avoid a perturbation. Something like, suppose I am carrying this cup, let us suppose this is just a glass and I do not want to spill the hot liquid in there, because it is embarrassing and it is also dangerous. If it is hot enough, it could cause injury for me, is it not? So, I want to do that. If I am walking without the cup, if I am just walking without the cup or with a pen, say for example, I am not going to have a heightened co-contraction level, or I am going to have relatively more activation of the muscle that is responsible for that movement, whereas in this case there is going to be a greater amount of co-contraction. That means we should suspend the reflex responses and activate the other muscle. So, this is again possible. So, that means co-contraction, right. This is again possible through descending inputs. Let us remember So, whenever I say descending inputs, where are these things coming from? These are coming from actually what are the various sites in which you could modulate the the reflex responses. There are only 3 places in which you could modulate the reflex responses, is it not? First is the alpha motor neuron, second is the spinal interneurons, actually there are too many of them, and the third importantly is the presynaptic terminal of the afferent neurons. Now, let us remind ourselves of what this presynaptic business is. If I would like to have an inhibition, right, it is possible for me to cause this inhibition postsynaptically or presynaptically, is it not? Postsynaptic inhibition is regular postsynaptic inhibition that is caused by inhibitory neurotransmitters, etc., etc. And we also saw a case of inhibition that is caused through presynaptic method. We discussed that earlier. This is like having 2 knobs, right, gross adjustment, or as we see in some of the instruments that we operate, gross adjustment of gain and then fine adjustment of gain. So, inhibition can be performed at a gross level for multiple sites using postsynaptic method, or selectively for specific neurons using or fine adjustments using the presynaptic approach. Okay. All these 3 are possible. Now, I could change the response to reflex by modifying the tonic excitatory state. If the tonic membrane potential, tonic excitatory state is at that level, for a given reflex amplitude it is going to take the membrane to that level of this, and there is going to be no response or response depending on what the threshold is. Now, if I change the descending input to take the membrane potential to that state, right, and I supply the same amplitude reflex or the same amplitude stimulus that causes the reflex, that could take the system to action potential and cause a response that is measured. So, depending on the where the resting state is, depending on whether the resting state is here or here, the response will vary, and the stimulus, let us remember, the stimulus remains a constant, the stimulus is the same for the same stimulus depending on the excitatory inputs coming from the top, coming from elsewhere, the response can vary. So, but that this is something that the the higher centers control, can control, possibly control. The reflex response is ineffective, then we can make it effective by changing the excitatory tone that is already present in the system, right. So, that is one. And let us also remember one more thing, that whenever the alpha motor neuron is activated, the gamma motor neurons are also simultaneously activated. We said that, and we call this as the alpha gamma co-activation. The earlier co-activation that I spoke just a few minutes ago is the co-contraction of 2 different muscles. This is alpha gamma co-activation, where fibers of the same muscle, extrafusal fibers and the intrafusal fibers of the same muscle are simultaneously activated. Okay. This we called as the alpha gamma co-activation. Okay. Now, let us remember what happens. We discussed this earlier, the function of the muscle spindle, is it not? When the fiber is stimulated, right, when the 1A afferent or muscle spindle is stimulated and there is a stretch that is, or it could either be mechanically stimulated or could be electrically stimulated, or when a stretch is caused like that, there is going to be sustained response. And we let us also remember that there is both dynamic sensitivity, that is adjusted by changing the input to the dynamic gamma motor neuron, and static sensitivity, that is So, depending on how I change the inputs to the dynamic gamma motor neuron and static gamma motor neuron, sensitivity of the 1A system, the 1A system can either function as a velocity sensor or a length sensor, is it not? So, that is the response. Now, suppose I am contracting the muscle, I am contracting the muscle. Now, what will happen in the absence of gamma motor input, right? I am causing a contraction of the muscle through electrical stimulation, and I am activating only the, so that means only the alpha motor neuron is activated, only the, if the alpha motor neuron is activated, what you will see is some length being measured, and the length being measured after the contraction is over. During the contraction this is silent. Why is this silent? Because the static sensitivity has not been adjusted, the gamma motor neurons responsible for changing the static sensitivity have not been activated. Because of this reason this remains silent. If I want to still measure length, what I should do? I could activate both alpha motor neuron and the gamma motor neuron. Earlier you see only the alpha motor neuron that is activating the extraphyseal fibers. Here simultaneous activation or simultaneous stimulation of both the alpha motor neuron and the gamma motor neuron, both the extraphyseal fibers and the intraphyseal fibers. When both are done, what you see as a difference from the previous picture is here it is silent, whereas here it is still measuring length. So, experimentally we have confirmed the important role of the gamma motor neurons, something to remember. Okay. I could adjust the sensitivity by, so but if I simultaneously activate some alpha and gamma motor neurons, I am going to get a response like this, which is considered normal response. This happens only in experimental situations, is it not? Okay. Now, another case is the case of long loop reflexes, the case of long loop reflexes. Now, what is this? This must somehow involve the higher brain centers. We will discuss what these higher brain centers are later, but for now let us just say that there is a response that is measured at relatively short latencies, which we are going to call as for want of better terminology as M1. Now, what is this M1? If the muscle is stretched, there is going to be an immediate monosynaptic response to contract that muscle through mediated by the 1A afferent system. Okay. So, 1A afferent activates the alpha motor neuron and that response is found. Say for example, this is what we call as H reflex, but if it also continues, right, there is going to be an improved response, a more contextual response that is modulated from by inputs from the higher centers, which is called as M2 or M23 or M2-3 etc., lots of names. So, let us not confuse this with the earlier terminology. Earlier we called the first response, monosynaptic response, as H reflex if it is electrically stimulated, right, and M response is the response that is directly coming through the motor neurons. M response stands for M for motor neuron. Direct activation of motor neuron causes M response. Here when there are multiple muscle responses, the first response is called as M1 monosynaptic response. M23 or M2 is a polysynaptic or a long loop response. Okay. The, say for example, the right hand of this individual is controlled by the left, the contralateral side, the other side, the left motor cortex, etc. So, the input is coming from there. There is the example that is given is what would happen in people with specific disorders where this function, this integrity is compromised. Please do check this. I am not going to explain this. Please do check this syndrome, Klippel-Feil syndrome. Please Google this and see what will happen if you activate one, if you stretch one particular hand, say the right hand muscle is stretched, M1 will be present in the response of the right hand, M23 will be present in the response of both hands. Why this happens? Please do check about that. Okay. By this, so again once again, by carefully stimulating individual systems or individual neurons or individual or groups of neurons and measuring simultaneously with of course synced responses at multiple sites, we are able to come up with hypothesis on where the pathology is. This is classical neurophysiology, this is how it is done. Okay. So, please do read about this, please do Google this and read about this yourself. Okay. So, one more thing, so let us also remind ourselves of the total of what is going on. So, alpha motor neuronal activity is, this is the alpha motor neuronal activity, it is going to get excitement from the cortical system, or unfortunately this also has the same name, primary motor cortex, which in future classes I will call as M1. It also controls gamma motor neurons, which changes sensitivity of the spindle, is it not? So, the external load, if it is stretching, right, force produced overcomes that, and length information is measured by the spindle, which activates this. So, this activation of the alpha motor neuron is not just through this or just through this, it is actually through a combination of both these pluses, is it not? So, let us see what happens, is it not? In the case of reflexes, it is only this plus that is acting. In the case of real everyday movements, what is actually going on in real everyday movements is a combination of this, but you are not observing which one of these is contributing how much. So, you are only observing the net output, you are only observing the activity here, you are only observing the activity of the length, you are only observing the force that is produced. But it is produced by a combination of inputs, how much of this is due to reflex, how much of this is due to what component is due to what cause is an important question that continues to be researched at multiple levels. Okay. So, in summary, we have seen monosynaptic reflex, we have reviewed that, we have seen the case of 1A interneuron, we have reviewed the case of Renshaw cells, inhibitory interneuron, and the 1B interneuron that causes inhibition of the homonymous muscle and also receives inputs from multiple sites, the case of stretch reflex and alpha gamma coactivation and long loop reflex pathways. We have also introduced the topic of flexor withdrawal reflex and crossed extension reflex, and we have discussed the concept of co-contraction. Okay. We have still not done co-contraction. Okay. We have still not done the case of oligosynaptic and polysynaptic reflexes, the cases that are called as tonic or tonic stretch reflex. Okay. And what is it? What is the difference between the regular stretch reflex and the tonic stretch reflex? What is tonic about the tonic stretch reflex? And tonic vibration reflex. We had to discuss once again the case of flexor response and crossed extensor response. These we will do in future classes. So, with this we come to the end of this class. Thank you very much.